Okay, so here's what we were talking about last time. We were doing vector surface integrals is what I like to call them. Surface integrals, well, because we're adding up over a surface, right? I mean, you got to call it a surface integral, kind of. But it is really fundamentally different. I think it has some very important differences compared to the scalar surface integrals that we saw previously, in that, from a certain point of view, the differential is a vector. Right. In other words, you might not choose to write it that way, but if you look at the part of what you might like to call the integrand, this in vector here comes from the domain. It's part of the domain, right? So I think it makes a lot of sense to group those, the in and the ds scalar, together and call that the ds vector, and thus this is how I prefer to think about these new kinds of integrals. I call them vector surface integrals, again, because the differential is a vector. Note also the integrand, also a vector. Right? Okay. All right. So we talked about several different points of view on these things. I won't go through that discussion again. But we do to make sure to be aware of these several different ways of writing what are, in fact, ultimately the same thing. Here's how, very often, we compute them. Right? This comes from a parameterization. So here's the example we talked through last time. We were a little bit rushed, so I'm going to do it again. So suppose you are interested in computing the flux. Recall the term flux is an alternative term for vector surface integral. Same thing, in other words. Okay. By the way, sometimes people will call these flux integrals. Yeah, same thing. Okay. All right, so how do you compute flux? Notice we were given a vector field. So there's our vector field. We were also given a domain here. There's a lot of discussion here defining the domain. There's your domain. And I want to talk about a certain aspect of the domain before we continue along. That domain, notice it says oriented downward. The language here is a little bit slangy. It's a little bit sloppy, but it's extremely convenient and very appropriate in a way that I'd like to talk about. So that's what we're going to talk about next. Let's talk about oriented downward. Here's a picture of our surface. Right, this is our domain that we're interested in. Recall that an orientation is a choice of which is what we're going to consider the correct direction through the surface. In other words, I want to know, we got fluid that's flowing through this surface. Which way do I want to think of as being the positive direction through the surface? It's an arbitrary choice, right? But it's a choice that has to get made in order to be able to answer the question. So here's the thing: there are two directions through this surface. Here's one of them. I could talk about, for example, at like, let's say that point, I could talk about that direction through the surface. And which means that sort of dictates that I'm, also going to have to make that same choice kind of everywhere on the surface. Same, in air quotes. So that's an orientation. By the way, it's really hard to draw orientations, right? I mean, if I wanted to draw the complete orientation, I would have to come over here to that back point and try to figure out how to draw an arrow that's coming out of the screen toward us. And it's just hard to draw. So I'm going to draw incomplete pictures. And, you draw enough of these orientation arrows, and it's pretty clear which orientation you're talking about, right? So there's one of them. The other orientation, possible orientation, would be the other direction through the surface. It should look something like this, for example. Okay, now here's the lingo problem. How are we going to distinguish these two orientations from each other, right? I mean, I have the luxury here that I can use colors, and so I can call them the blue one and the purple one, and that's very nice, right? But y'all won't have that in general, right? So how are we going to distinguish these in words, in the language, right? So I guess I could write down an equation for, as a function of where you are on the surface. I could write down an equation for the orientation that I mean. That's a tremendous amount of work, and maybe that's part of what I don't know how to do and need when I ask you a question, maybe that's part of what I want you to actually do. Plus, it's a big pain. Right? So here's where the lingo comes in, and admittedly, this is a little bit sloppy, but you can look at these orientations and you can find what I'm going to call distinguishing characteristics. Right? So let's look at this, what I'm going to, again, loosely call the blue orientation for just a moment. Those blue vectors all have a certain feature in common. And furthermore, the feature that I'm thinking about, that all these blue vectors have in common, is something that none of the purple vectors have. Right? And that is that these blue vectors are all pointing at least somewhat up. Right? They're not pointing exactly straight. I mean, I guess one of them down at the vertex is pointing exactly straight up. Vast majority of these vectors are not pointing exactly straight up. But if I say they're all sort of up-ish, right? Upward, loosely speaking, right? Then you know what I'm talking about. And then, by contrast, these purple vectors here, they all are pointing, well, somewhat down. Not exactly down, of course, exactly at the vertex, yes, exactly straight down. But everywhere else, they're just somewhat down-ish. And again, distinguishing in the sense that they're all doing it, and none of the others are doing it. Right? So that's an example of what we're saying when we make a sloppy statement like this. When we say oriented downward, it's not exactly downward, right? And a common mistake for students to make, a very common mistake, and this is just dramatically nonsense, is for students to think, oh, he said downward, therefore the orientation vectors are all this. Well, that isn't an orientation, right? Orientations are a choice of unit normal vectors. You have to give me vectors that are perpendicular to the surface, right? So that's not even a candidate. That doesn't make any sense, right? So you have to look at the language and think about how does that language distinguish the two possibilities from each other, and then choose the one that's I'm going to say obviously being referred to. Yeah.
What if it's a cylinder and the vectors are pointing?
Yeah, great question. So that's the next thing I was going to talk about is notice that this language, your point is that this language doesn't always, downward versus upward doesn't always distinguish, right? So an even easier example than that is what if you had a vertical plane and our two orientations are this and this. Well, you could, the way I have it drawn here, you could say to the right and to the left. And then if it's a cylinder, you can't say upward or downward. Quite right. You can't say left or right. Right. So here's what I would do. I would say, well, look, come on. Some of them are what you're going to want to call inward, and that's by comparison to the others, which are outward. So you kind of have to tailor your language choice appropriate to the circumstance. Again, you're looking for what is a distinguishing characteristic between these two different choices, and then make that reasonable choice. Or if someone has made the choice of language, then you should interpret it accordingly. Yeah, does that make sense?
So how do you know which one should be negative and positive?
When you say oriented one way or the other, here, if I were to say oriented outward, then that is saying that these are my unit normal vectors, right? And that, therefore, is what I mean by a positive direction. And notice that if the flow field, if the F were like this, right, this dot product would be positive, thus indicating that that's the positive flow direction. Okay, right. So heads up about that language. It's a constant source of confusion. Okay. Proceeding along. So now we talked about the following point last time, so I won't go through the whole thing again. But when you parameterize, it's hard to tell if you're parameterized in the correct direction or not. So this parameterization that we choose, I choose because it's the only way I can think of to parameterize that surface. Right? It's in some sense harder. It's certainly less geometrically intuitive when you parameterize a surface compared to if you parameterize a curve, where we can think of, I'm tracing it out in time, right? The surface, it's just not the same. So you parameterize and you go through the calculation and you see what your normal vector is. And in this case, I see that my normal vector has a positive z-coordinate, that means that between these two choices, I must have oriented this thing in the up-ish direction, right? I inadvertently parameterized upward. I didn't know it as I was doing it. Forgive me, it's hard to tell, right? I mean, it was an accident, right? So I parameterized it backwards. I should have parameterized downward. I accidentally parameterized upward. I parameterized backwards, and we acknowledged this last time by multiplying by -1. Right? Neat fact, surface integrals, just like vector line integrals, you parameterize it the wrong way, you get the exact negative of the answer. Okay. All right. Let me pause on all this for questions. Anybody? Everybody happy? Two other quick notes. Reminder, we talked about this last time, but I'll say it again. I don't expect you to write, a whole paragraph there when you do this. If you find yourself having inadvertently parameterized it upside down, backwards, however you want to say it, you can document that by saying parameterization wrong. So, and then circle your minus sign, right? This is perfectly acceptable documentation of your reasoning. And note how quick that is. Okay. All right. One last little quick thing I guess I'll say. Oh, two things. Okay, so the first last thing I'll say is this integral here. Hard integral, you're doing it over a disk in the UV plane. So the bounds are going to be all messed up, right? And this isn't all that bad, right? But once you do an integral over a disk, the outer integrand is going to be ugly. So notice, just because what you're doing is a surface integral problem doesn't mean it's not also a polar coordinates problem, right? So always think, once you get once you do your pullback and you get your double integral, don't forget to think strategically about what's going to be the most convenient way to actually compute that double integral. The other thing I wanted to say real quick, and this was just another discussion of language, very, very, very quick. So again, we distinguish these two orientations by upward versus downward. It would not be unreasonable also to call them inward versus outward, right? Inward versus outward is a great choice for example, if you're talking about a sphere or something that's, encloses an inside and an outside. So anyway, just another language option to kind of be on the lookout for. Okay. So every so often you get lucky. I like to point out when examples of this kind of thing that can happen. So always be on the lookout. Y'all recall that I made this point. I think this is a huge point when you're talking about integrals, double integrals, triple integrals, to look out for symmetries. Right, huge number of integrals. I shudder to think the quantity, the numerical quantity of integrals that in my undergrad experience, I was able to say this is zero by symmetry. Right, it saves me tons of trouble. So I hope y'all will have benefit likewise. So not terribly different from that is just general geometric good fortune. So here we've got a surface that's a part of a certain plane, but it's a part of that plane that satisfies that inequality. And here's a picture. It's kind of a round-ish thing. Note, it's not a disk. These exponents are 4s, not 2s. Right? So that's kind of an ugly domain, really. Here, let me zoom back in. Sort of an ugly domain. We've got a vector field. And yikes. Okay? I mean, look at that monster. Right? So sometimes, again, you get lucky. Try to capitalize on your good fortune when it comes to you. There's two bits of good fortune here. One is every point on our domain is in this plane. Every point in that plane has y equals to 3. So for our entire calculation, y shall be 3 everywhere. And I don't really care what the vector field's doing over there. I'm looking at the flux here. Right? So if y is 3, notice that means that the second coordinate of your vector field is 0. So you can just go ahead and replace that with 0. Just boom, first thing. Very nice. Right, so be on the lookout for that. Another little bit of good fortune, second little bit of good fortune after your second coordinate turning into 0, is to think about your differential vector here. Now again, we have lots of formulas, and you can parameterize and plug and chug, and that's fine, and it'll get you to a fine answer. It wouldn't even be all that bad, but again, sometimes things are even easier than that. I can draw a picture of my ds vector. Right, my ds vector, I mean, it's like that, right? It's perpendicular to this surface. The surface is in this plane. That normal vector is clearly pointing straight in the y direction. And vectors that point straight in the y direction are really easy to understand. Right? The x and z coordinates are both 0, and the magnitude is the y coordinate. So there's my ds vector. That makes that second part easy. So now, having taken advantage of our two little bits of geometric good fortune, notice that the dot product that I need to compute at this point is conveniently 0, right? So that product is 0, that product is 0, that product is 0. I'm adding up a bunch of zeros. This integral is 0. And I didn't really have to do any real work at all. So be on the lookout. Stuff works out really nicely sometimes, right? There's a bunch of, the world is highly asymmetric, but it is full of things that, little bits here and there that really are very symmetric. There's lots of spheres and circles in the world. There's lots of planes in the world, flat things, right? I mean, these are a lot of things to capitalize on when you can. Okay. All right. So I want to extend an analogy here. Let me first. Okay, so I've made some vague references in this class to how a lot of the theorems that we're going to talk about in this class are really kind of the same theorem, right? Y'all remember this whole speech I gave about how there's like 6 or 7 different theorems that really are, they're all special cases of one theorem. They're all special cases of what's called the generalized Stokes' theorem, and we will not be able to discuss the generalized Stokes' theorem in this class. It's too sophisticated. What we will be seeing is the several special cases, certain kinds of integrals in certain contexts look a certain way. Right? And those special cases are, in fact, we've already seen some of these. Right? Green's theorem is a special case of the generalized Stokes' theorem. Fundamental theorem of line integrals, fundamental theorem of calculus. These are all special cases of the big theorem that we can't talk about. That big theorem that we can't talk about is about integrals of differential forms, something called differential forms. And we can't talk about differential forms. So anyway, in these different contexts, we're, in all those cases, looking at integrals of differential forms, and I just want to point out what integrals of differential forms look like in these special cases. And it turns out that in the appropriate context, an integral of a differential form is a vector line integral on a curve. That's really what you're computing when you're computing a vector line integral. It is an integral of a differential form. When you are computing a vector surface integral, you are computing an integral of a differential form. It's a different kind of differential form in a different context. It's still an integral of a differential form. So, why this matters to y'all? I think this is a really useful sort of learning point. If, as you're trying to make sense out of all this stuff, even though we're not going to talk about differential forms at all, the fact that these two different things are all special cases of the same thing makes it perhaps not unsurprising that there are strong analogies between these. There's a very surprisingly, kind of shockingly really, strong analogy between vector line integrals and vector surface integrals. And I just want to point those out. Now, we're not computing the same stuff. Here, arguably, we're computing work. Right? Here, arguably, we're computing flux. How much fluid is flowing through a surface versus how much work does it take to compute, or does it take to exert some task. Physically, they look very different. But let me go through the analogies now. First of all, let me do one at a time. Here's our picture of a vector line integral. You see we have our curve, and then that curve has been parameterized. I pull back to a dt integral, and we have all these formulas involving the differential dx. All that's old news. Nothing new here. All old news. And then we have all these different versions of when we're doing vector line integrals. That's my favorite notation. This is the book's favorite notation. This is, for many students, their favorite notation, because this is the parameterized plug and chug notation. Don't forget that dot products with unit tangent vectors are components, etc. Okay. Surface integrals. You take a piece of surface, you parameterize. This time we parameterize from 2 dimensions. Right? We have various objects in discussion. Here are the vector differential and its various equations that we know about it. And looking at flux integrals accordingly, there are a bunch of different versions of different ways that you can write flux integrals. Again, my favorite, very often the student's favorite, because it's parameterized. The book's favorite, aesthetic preferences. Okay, so now let's talk about the analogy. So again, we've seen all this stuff, but I think it's fascinating and instructive to see how strong the analogies are, and here we go. Notice in both cases, we are parameterizing. In both cases, we are doing pullbacks into Rn. Well, R1 on the left, R2 on the right, but we're still doing pullbacks into Rn. One thing I left off the diagram here. In each case, there is a little piece of the domain that we talk about, dt over there. Over here, we talk about a little piece of size du dv. By the way, I had intended to color code these as I went through. Let me do that. Let's see here. So, for color coding purposes, I guess I don't really have any yellow stuff. So the green stuff, green. Okay. Now let's see. In both cases, we take that parameterization and we do a certain kind of a derivative of it. Now, in the case of the parameterizing a curve, the derivative of the parameterization is the velocity vector. Again, old news. For surface integrals, when we take the derivative of this, we get a couple of partial derivatives. We get the partial with respect to u, we get the partial with respect to v, and what does that have to do with surface integrals? Well, we take their cross product, and so forgive me, I'm taking a little bit of a liberty with the analogy here, but I'm going to call in a derivative of the parameterization. It's a cross product of the derivatives. I'm going to call that a kind of a derivative. So there's a derivative. And now again, let me fill in, where that shows up down here. Right. Notice how everything's laying out exactly the same. Right? The analogies are crazy strong. And let's continue. In each case, there is a corresponding unit vector. Let's see here. Color choice. I guess I'll use purple. Here's the unit vector in the direction of the derivative. Here's the unit vector in the direction of that derivative. Right? Notice how that shows up sort of analogously. Right? The colors lay out in exactly the same way. These different things, different appropriate to their context, play highly analogous roles, right? And you can continue on with this. Let me just do a little bit more. I'm a big believer, as y'all know, in the vector differential, the dx vector over there, the ds vector over here. Right? Again, the colors layout is exactly the same way. Maybe I'll stop there, but the analogy is extremely strong, right? And it's worth paying attention to. Again, a couple of reasons. First of all, this is a glimpse into an extremely deep discussion, an extremely deep fact that, again, we don't really have access to, wouldn't be appropriate to have that conversation in the context of Math 212, but this is again, you're seeing some really important ideas in here. So that's one thing. And so if only as a cultural point, I think this is really worth knowing, right? But here's how you're going to take advantage of this to do better in this course. If you find yourself maybe not 100% understanding vector surface integrals, and there's certain things you never really know, what's the deal with that thing anyway? A lot of students, for example, get confused about the capital N vector. What's the deal with capital N? Okay, well, it's the vector surface integral analog of velocity, right? So it plays roles just like the velocity does. Right? So if you want to understand this capital N vector, think, okay, well, look, I see how velocity relates to the parameterization and allows me to do certain things that I need to appropriate to the to vector line integrals. Well, that's advice on how to think about how capital N relates to the parameterization it comes from and how it relates to other things involving the surface integral. Right. So there's a lot of good sort of you can sort of make sense for yourself out of things just by thinking, taking the thing that you don't understand, relating it to something that hopefully you do understand, and then using that understanding to fill in what you didn't understand. Okay. So, like I said, I'm a big fan of that concept. Okay, moving along. By the way, this whole discussion here is not in the book. This is a supplemental thing that I think y'all would benefit from. Okay, moving along. So, y'all remember when we were doing vector line integrals, and there was this awkward conversation that we had about coordinate line integrals? Kind of a weird notation. But anyway, it's something that had to get said. Again, it's out there. It's in the world. People use coordinate line integral notation all the time. Well, we're going to talk now about coordinate surface integrals, and it's analogously out there. It's in your future. You're going to see coordinate surface integrals. And it's also sort of analogously very important in deep ways that we won't be able to see in this class, and also very relatable back to things that we do understand in this class, namely vector surface integrals themselves. Okay, so just a quick reminder, old news from vector line integrals. And when we made the jump to talking about coordinate line integrals, I asked the question, okay, weird question, but if I were to look at these coordinates of my dx vector one at a time, right now notice we're looking at our vector differential. If I looked at its coordinates one at a time, what should I call that? And the idea of our choice was that we should call that dx. And it seems reasonable. I mean, notice that there's this sort of cancellation-ish, right? It's not really, but you know what I mean. There's this faux cancellation there. And also, if you look at what that coordinate is representing, right, your vector differential really does have coordinates. And we call that dx because it is the x-coordinate of our position differential vector. Okay. All right. So then I threw a point of view on y'all that a lot of students find weird, but here's where it's going to start to become important, and that is we can think of dx in a different way here. Instead of thinking of dx as the amount that x changes, right? So change in x. Instead of thinking of it that way, that's going to seem weird, but we could think of it instead as, well, look, there's our dx vector, there's our position differential, and if I were to think in terms of how that sort of projects, if I were to look at its shadow down here in the xy plane, right, I just trampled what I need. There is a corresponding size, and there is a corresponding what I'm going to call a sign. This vector here, this green vector, has a direction that it's going that way. And if you take that direction and look at how that direction shadow looks down here in the x-axis, it's pointing in the direction that the x-axis goes. Right? So, weird point of view, I freely acknowledge, but you can think of the dx scalar as being a thing whose magnitude is the size of the projection and whose sign tells you whether your piece of curve projected the right way along the x-axis or if it were negative, right? Imagine if you continue along the curve here, and now notice over here I'm going this way. If I look at that little piece of curve, it projects that way, which is going, I'm going to again loosely call the wrong direction, right? It's going to the left. The x-axis goes to the right. It's going in the negative direction. Okay, so this is one way to think about the dx coordinate differential. Seemingly a pointlessly awkward way to think of the dx coordinate differential, but it's going to turn out to be valuable. Think of it as a magnitude, a size of a projection and an indication of rightness or wrongness of orientation. Okay, now why do we care about this? And it's because if you insist on thinking of the dx coordinate differential as being a change, then this point of view that you hang your hat on will not make any sense at all when you start wanting to think about surface coordinate differentials. It just doesn't make any sense. But this idea of projections does. Right? So this projection point of view here is what's going to make sense for surface integrals. And here we go. Here, by the way, quick reminder, what we did, where we started off with line integral coordinate differentials, was we looked at our vector differential, we wrote down our formula for it, which we can expand, and then we asked, individually, what do those coordinates mean? Okay, so the analog of that for surface integrals is this. There's our coordinate differential. Our surface vector differential, ds. These are our existing formulas for it. It's on a couple pages back. This is how we expand that out. Now we're just going to ask the question, what do these coordinates mean one at a time? What do they look like? How do I think about them geometrically? And I'm going to look at the third one here for kind of geometric convenience. The argument that I'm about to show you generalizes very nicely to the other three coordinates. So let's ask, what does partial xy, partial uv look like? And you can't think of this as a change. How much does something change as I move along the surface? That doesn't make any sense. What we can do is ask, is this a size of something, and does it involve a projection? And it turns out that works out just perfectly. So here's how you can think of the projection. Now, real quick, first of all, here's our parameterization. Right, so we've got some surface over here. Here's a little piece of that surface that we're looking at, and here's the pullback little piece of surface, du dv. If I were to think about the projection of that little piece of surface, the projection down into the xy plane, and now just for sort of visual reasons, I'm going to rewrite that projection as, new function, composing to the right. Note, I'm not really doing anything different. I'm just redrawing the same picture. Right, here's the projection in the xy plane. You can think of the xy plane as being sort of the floor over there, or you can think of it as being its own little world, and I just want to think of it that way. When you do a projection, right, notice the end result is that you have x and y as functions. It's a composition, but as functions of u and v. And so check it out. We have x and y as functions of u and v, and this little fellow right here, old news, we already know that's the thing whose magnitude is the stretching factor. That's how we compute stretching factors and change of variables. Right? So if that's your stretching factor, jumping out over here, that's your stretching factor. And notice that what we have here, if that is the stretching factor. There's a little piece of size in the UV plane, du dv. Input area times stretching factor gives you output area. Oh, the stretching factor is the absolute value, sorry. So the absolute value then is output area. It's this little area right there. Namely, it's the area of the projection. I mean, it literally, right? It's wonderful how everything kind of fits together like this. But this expression that we were interested in, this expression that we were interested in is a thing whose absolute value, that thing, its absolute value is the area of the projection of the piece of surface. Just like this thing over here, dx. Okay? This thing that we're trying to make sense out of over there. That is a thing whose absolute value is the size of that projection of that little piece of curve. So the analogy is very, very strong. The calculation's a little weirder, a little bit less sort of viscerally familiar, right? But the result is extremely analogous. So for your consideration, now let's talk about the pluses and the minuses here. When we're talking about the dx, when dx is positive, that means that we're projecting in the what you might call the correct direction. Whereas if dx is negative, that just means that the curve has moved around in such a way that we're now going backwards, in that the projection makes that arrow project backwards. Right? So plus means you're projecting the right way, minus means you're projecting the wrong way. Is that what is going on here? It turns out, yes. Again, you got to look at the picture the right way, but let's not forget where these things come from. This dx, this partial xy, partial uv. That thing, if it's negative, don't forget it's the third component of your capital N vector. That means it's telling you about which direction your orientation points. And big surprise, if this is negative, it just means that this is where did I write this? It just means that this thing here is pointing downward. Third coordinate's negative. It's pointing downward. And if the orientation is pointing downward, then that means that our little piece of surface, when you project it down, our little piece of surface projects upside down. It's projecting the wrong way. Right, so now the algebra, the geometry looks a little bit different. Here's what it looks like when a curve projects the wrong way, or when a curve projects backwards. It's going to the left instead of to the right. When a piece of surface projects the wrong way, it's pointing down instead of up. Right, so you can just see it on your surface when you're looking at a piece of surface. If your surface has wrapped around so that the surface is upside down and your orientation is pointing downward, yeah, well, that means that coordinate of the vector differential is going to be negative, just like we're seeing here. Okay, all right. So a lot to say about that, but let's get to the punchlines. So reminder, we're trying to figure out. Let me go back to the. We're trying to figure out our vector differential one at a time. What do the coordinates mean? We focused our attention on this one, but whatever, the analogous arguments apply to these, and that's a good exercise. I encourage y'all to think through these two that I didn't have time to talk about. Right. So vector differential, looking at the coordinates. What do they look like? What should I call them? So here we are. These are those coordinates. What do they look like? What should I call them? Well, I mean, here's a thought. This thing here is telling me about the size and orientation of the projection in the XY plane. It's telling me about what area in the XY plane looks like. When I project, oh, come on, I wanted the pencil, sorry. When I project down into the XY plane, it's telling me about little pieces of area in the XY plane. So how about dx dy? Seems like a really reasonable choice. That's how we talk about areas in the XY plane. This is an area in the XY plane with an orientation, a plus and a minus. Right? Area is always positive, so this is a signed area. Right? But dx dy is the natural thing to call it. Just like here, this thing, what are we going to call the oriented little projection there? Well, it's a piece of the x-axis, so how about we call it dx? Likewise, this thing here is a piece of the xy plane, so we're going to call it dx dy. And so that's the choice that we make for all of these. So this thing we're going to call dx dy. Whoops, I wanted to highlight. That thing we're going to call dx dy. And analogously, these other coordinates, and here they are, we're going to call those dy dz and dz dx. And now, and again, reminder, let's go. I mean, there's so many things I have to, sort of analogies I have to keep track of here. Why are we doing all of this? Why are we trying to give names to our ds vector? Well, it's because we're trying to figure out what to do. Oh, colors. What to do with an integral. If I have integral PQR dot ds vector, surface integral. If I want to do an integral of vector field dot ds, if I want to crank out that dot product and write it in coordinates, I need to have names for what to call the coordinates of that ds vector so that I can actually write down how this dot product multiplies out. Right? We did that with vector line integrals, and we got this, fairly unpopular among students notation, p dx plus q dy plus r dz. Well, now we're prepared to do that with our ds vector. We now have names for its coordinates. And here's how that plays out. Our ds vector. There's the old notation that we used for the ds vector. Old formulas for how to compute, when it comes time. Here's the new names that we've just decided to give those based on observing how these are in fact really projections. Right? We're projecting into the coordinate plane. So we have then a way to rewrite ds. There it is. Just rewriting ds. Recalling, of course, that our vector field was PQR. And now this dot product that we had very neatly, compactly, compressed down into this very, very pocket-sized notation f.ds, right? How efficient, right? How convenient, right? But if you want to crank that dot product out, now you can totally do it in coordinates. And again, it's pretty unpopular among students, and I sympathize. But that's what that dot product becomes. And so this is a coordinate surface integral. An alternative notation for writing flux integrals. And again, we've never defined, before moments ago, we've never defined these things like what is an integral over a surface of a function times dx dy. That's weird. We've talked about integral dx dy before, but that was when we were doing, we didn't have a surface, we just had a region in the xy plane. But now, what do you mean do a dx dy integral over a surface? That's not familiar. Likewise, we've done integrals over surfaces before. Yeah, totally. And our differentials were either surface area, which is not this, right? dx dy is not the surface area of that. This is, something about the area of the projection of it to some axis for some reason, right? We've talked about surface integrals with vector differentials. This isn't a vector, right? So this is a brand new and weird thing. And I've got to write down then what the formulas are for these weird things. Now this is just repeating what we've got written above. But when I write integral over a surface with coordinate differentials dx dy, that's what I mean. And the reason why I mean that, again, this is just a recopy. If I can, sorry for the smallness, but it's just because we've already agreed that dx dy really ought to be that thing. So this business down at the bottom of the page is not new. I'm just taking this already agreed upon rewrite and just plugging it in there. I mean, there's nothing, that's not new. But again, it's got to get said. Okay, so given your preferences, which would you prefer to use to write down a flux integral? Which one of these do you like better? This one's compact. This one is, in some sense, physical. Right? We can talk about flux and thinking of surfaces and orientations and fluids flowing, and that's physical and relatable and compact. And what's going on over here? There's not really much going for this notation, right? So that's from a Math 212 point of view, I think this is pretty undesirable, and I don't encourage you to use it. Right? I mean, why would you? Right? So again, just like with vector line integrals, the reason that you have to know this is because some people love it and use it a lot, even when its powers are not particularly evident. So you're going to see this, and you have to know what it means. The other reason, and again, kind of a cultural point, these are, in ways that we can't talk about in this course, actually very powerful things. And side note, if you're kind of wondering what are these things and how is it that they are so powerful? These are differential forms. This is effectively an integral of a differential form, and so were coordinate line integrals. Those coordinate line integrals that I trash talk, right? Because I don't like it. What a pain, right? These coordinate surface integrals, right? Annoying. Goes all the way across the page. Very clunky, right? This is what integrals of differential forms look like, and there are powerful, amazing things that you can do with this notation. So I don't want you to think that I actually dislike the notation. Not at all. It's just in the Math 212 context, maybe not so much. Okay. Alrighty. How we doing? Anybody on board? Okay. All right. For example, I mean, look, if you're out there in the real world at some point, you see an integral that looks like this. We all are aware, we've seen bazillions of kinds of integrals at this point. Let's count just for fun. Single variable integrals, double integrals, triple integrals, scalar line integrals, scalar surface integrals, vector line integrals, vector surface integrals, and now coordinate line integrals and coordinate surface integrals. We have seen 9 really, truly different kinds of integrals that are fundamentally different critters. That's a lot, right? So when you find yourself seeing an integral, I mean, I hope it goes without saying, but the very first thing that you should ask yourself is, wait a minute, what is this? Which kind of integral is this? And then figure out how to deal with it accordingly. So when you notice that your differentials are coordinates like that, and you're thinking, oh, good, double integral, right? Up, slow down. You got to think about your domain as well, right? This domain is a surface, not a region in R2. If this were in the YZ plane, then yeah, fine, but it's not. You got a surface domain with coordinate differentials. This is a coordinate surface integral. And you have 2 choices. on how to compute this thing. One thing you could do is say, I have a definition of coordinate surface integral. There it is, and here's the formula, and you can plug and chug, and that's totally fine. And sometimes that's the right way to think about it. I just want to point out another thing you can do is remember what the ds vector is. Remember that the ds vector is, oh gosh, I've got to get in the right mode. Dy dz dz dx dx dy, right? And so this integral that you're looking at, g dy dz, it's something times dy dz. Specifically, it's that times dy dz. And so given where dy dz is, I mean, that's where the function's got to go. Therefore, this is your vector field of which you're doing a vector surface integral. So if you want to reinterpret your coordinate line integral as a vector surface integral, I said line integral, sorry. If you want to reinterpret your coordinate surface integral as a vector surface integral, this is how you do that. Okay. All right. I'm sorry. I went 2 minutes over. Sorry. We'll pick up here next time. See y'all later. Have a good day. Yeah.